In today's video, we're going to cover a novel neural dynamic architecture called Continuous Thought Machine from Sakana.ai. I'm excited about this architecture for two main reasons. First, because it bridges two of my favorite research topics, which is machine learning and neuroscience. And second, because this architecture brings something that is lacking in the frontier model right now, which is the time domain. For those that don't know me, I'm Yassine, a published researcher and machine learning practitioner who loves to teach. Do consider subscribing to the channel to learn technical topics related to machine learning. The main architectural contribution the CTM bring is that the model now has a time dimension which works with what is called ticks. These ticks are decoupled from sequential information within the data. The ticks also allow the model to do multiple computation on a single data point to reason about a task. Task includes, for example, maze traversal in this paper or object recognition. Throughout the time-bound reasoning process, different neurons modeled as MLPs are synchronizing together to model the latent representation of the information. This gives rise to a rich interplay of interaction between data, history, neuronal activation, and attention. If we look at an overview of the whole sequence of steps, we have the following. First, some elements goes into a synapse model that combines signals from every neuron together. The input to the synapse model is a bit complex. It's a mix of previous ticks post-activation and previous ticks outputs. But the end result of this step is that a new, what we call pre-activation point, get created for each neuron. While going through the steps, we keep a moving window history of those pre-activation, which are then fed to a neuron level model for each neuron, which is an MLP. This MLP will then output what we call a post-activation that will be fed back to the next tick input. These post-activation continue their journey into the synchronization matrix calculation, which compare the oscillation between neuron pairs. The sample latent representation here is then used as a literal output and as the input query for an attention matrix that accepts input data. This modulated output with attention is what is being fed to the next tick for the synapse model. And around we go over ticks. A funny thing here to note is that the data is almost secondary in this circular system. We have a lot of ground to cover in this tutorial, so I tried to pack as much information as possible from the article, from the notebooks, from the demo that they have. Feel free to jump around with the table of content. We're going to review the architecture of this model, the vision result of the 8 experiments they conducted, and a few selected notebooks that were open source to understand the structure fully. Throughout this tutorial, you will see me draw around a free digital whiteboard called TealDraw, who are kindly sponsoring this video. If you watched the stream or my tutorial for the past year, you saw me use this extensively because it just works so smoothly. My workflow is usually to take a screenshot of whatever I need to dig into, and then to make a collage of everything that is relevant with explanation scribbled all around. Two features I really like is the freehand drawing tool here, because it's very simple to use, but it has all the features that you actually need to explain something complicated on the screen. The other thing that I really like is the arrow. I like to draw them like this, but when I have to make a diagram that kind of follow some structure, I like to use these, right? And then I can decide where I'm going to put it, and then just follow the structure. And then you can you can edit the arrow. There's a lot of engineering that went into these arrows. They also have an SDK if you are a developer and want to add a whiteboarding functionality to your app. It's all React based. So what you're looking at right now is a prompt-based AI drawing tool where you're literally going to prompt, and then there's agent that will leverage and use the TealDraw canvas to build with the shapes, the drawings. In this case, it's a cat. So you can get pretty creative with this. So to test it out, you can go in tealdraw.com and you're going to be met with literally the canvas straight up. And you can also go to tealdraw.dev to play around with the SDK. So check out the link in the description, and big thanks to them for making this technical tutorial possible. Before jumping into the architecture, why even go with neural dynamic models to begin with? Most of the architecture in deep learning simplify away two core aspects of how the brain works. The first aspect is the temporal processing of information, which is kind of a limiting factor for a biological brain because it works with many different cells working together. And the second one is synchronization, or communication between neuronal population. This lack of temporal processing prevents models to use a mechanism that is key to how biological brain function, which is neural synchronization. These synchronization events lead to additional computing phenomenon for biological brain, like spike timing dependent plasticity. This process is a biological one that adjusts the strength of synaptic connection between neurons based on the precise timing of their action potential. The second synchronization event is neuronal oscillations. These are rhythmic or repetitive pattern of electrical activity produced by neuron in the central nervous system. These oscillations can occur in various frequency range and are associated with a wide array of cognitive process and brain state. Now, you might be asking yourself if we even need these things to begin with, since the model are currently performing well, and you can make the case that we're not trying to reproduce what the brain is doing, but we're trying to create intelligence. The argument from the authors is that yes, it actually matters, and they state that human intelligence is highly flexible, data efficient, it's fluid, and that it extrapolates well to unseen circumstances and exists in an open world where learning and adaptation are tied to the arrow of time. Just beautifully well put. Also, just to note, the last author of this paper is actually one of the other from Attention is All You Need, right? So I think it's a pretty important paper just in general. So let's take a quick peek at what this model can do using their interactive demo. You can try it out yourself. It's in the description too. There's two things that I want to show, which is the two most important experiments that they ran, which is the maze one and then the visual kind of object recognition thing. So the maze one, basically you start somewhere, right? I think it's the red dot, and then you have to go somewhere, which is the green dot. And then you have to figure out how to go there, right? And this task is kind of hard for transformer-based architecture because of the 2D nature of the thing. And you can kind of hack it out by having the model output the program that they can run, or having position embedding within it. In their case, they're doing none of that. So basically you have the continuous dot machine, and then they have no positional embedding, and they can only output one of 5, I think, up, down, left, right, and then wait. So that's kind of the idea, right? And like you can test it out here. So let's say if I want to move, let's say the green one, the graph that you see over here are like the attention heads and what are they focusing on. So that's the basic idea of it. This one I think it's gonna be a bit hard. So let's say we put it here. You see how we can make it slower. Run again. You see how it's making its way through it, and then like it's trying to, with the attention head, explore a bit further down the road. So like you see here, like this one is like observing a bit more globally. This one also, and the other ones are a bit more kind of local. So let's say we try to make it go here. We'll analyze the stuff and then try to find an optimal path. Almost got there. Yeah. So that's the idea of here. The next one that is pretty interesting is that it's just an imagenet thing. So there's nothing like wild in this specific experiment. It's just that now with how the model function, throughout the step, you can see what it is focusing on. And because of their implementation, you can see how certain they are about the actual label. So if we look at this one in particular, you see here at the bottom left is like all the label that have the most likelihood of being that as per the model. And like here you can see when it's purple, it's like it's not the right label that it thinks of, and when it's green, it's like it's actually the right label. And then like the height of this is the certainty of the model. So it's fairly certain that it's something, which is I think is a race of dog, and it's like iterating over ticks here. What we see here, right over there, is all the attention heads and what they're kind of focusing on, and you can see it like this is, I think this is the global one. You can see where it's focusing on for this attention head over time, right? Because remember, throughout the ticks, it's looking at like one image again and again and again. And it's going through a cycle that we've seen a bit at the start. We can look at another one here that it got right. So you see it was not certain at the start, but after a few ticks, it was fairly certain. So it's certain throughout because like the label that it has a very high like expected probability. Now that we have a good idea about why neural dynamics is a desirable framework for artificial intelligence, let's explore the CTM architecture. The 3 main elements that guide the CTM architecture are the following: decoupled internal dimension, neuron level models, and neural synchronization. That's the 3 kind of pillar that they use to make this architecture. So let's explore them, keep them in mind. With the overview of the architecture, we're gonna dig into like their main figure. we have this graph, this beautiful, beautiful graph. That is actually very confusing the first time you saw it, because it's a recurrent kind of architecture, but like it's not recurrent through the data, it's recurrent through time. It's decoupled, right? Like this is one of the three things we talked about. Because it's recurrent through time, the data is kind of secondary, which is a bit weird, right? Like if you look at the RNN, the recurrence is through the sequence in the data, right? So it's kind of easy to have a nice graph of it. You can start it literally anywhere. You can start it at the data if you want to, but in their case, they want to start it at the synapse model, which kind of makes sense, right? So the synapse model is one that will take the information from like all the neurons and kind of like mix them together to get what we're calling a pre-activation, right? So it's kind of weighting like all the neurons activation together in some sort of way. The input for this is a bit weird because it's the post-activation from the previous tick, right? And then not just that, but also the output that went through the attention layer from the previous tick. So that's kind of the setup, right? What happened at tick 1? It's complicated, but it's kind of a learnable initialization that they're doing at tick 1. So don't worry about tick 1. Let's assume we already have some ticks going. So it's the post-activation, what we call post-activation, stuff that happened after the neuron level model gets sent over there, right? So we're at the first thing, and there's already stuff from step 4 and 10 that start to pop off. That's just the nature of a thing that is cyclical. So all of these get like kind of weighted together in what we call a synapse model. The synapse model is actually a unit, right? It has this structure. We're gonna go through it in a few, but like it's just a unit that is over there. Then what happened is that these pre-activation, right? Like you get one at every tick, and then like they get stored in some sort of history per neuron. So each of the neurons that we have here have some history. You keep actually a window, right, of some history, and this window is kind of moving through time. So like you can kind of fall off like the very old pre-activations, and all of these pre-activation then goes into per neuron like a model just for them, right? So for each neuron there's a model. It's a MLP. It's like 2 layers, right? Depending on the implementation, but here it's like 2 layers that takes like the history for a given the history of pre-activation for a given neuron, and then they will output what we call a post-activation. So the post-activation is the pre-activation with the history that went through that neuron level model that has learnable weight for this specific neuron, and this is what the output is. The one thing that is interesting is that throughout the whole experiment, you see that they're trying to get grounded as much as possible in how the brain works, right? So you have this is the whole thing, right? And for the neural level model, it makes sense because it's a bit confusing, but an actual neuron in an artificial neural network is not close to a human neuron because it cannot learn XOR, right? That's the whole, you have to have MLP to learn XOR, but the human neuron can. So a human neuron look more like an MLP that an artificial neuron look like a human neuron, if that makes sense, right? So this is, in my view, what they're trying to model here. So you have a neuron which is an actual MLP, which is made of a bunch of artificial neuron that makes like this artificial biological neuron. So that's the idea, right? So you have the post-activation, and then the post-activation goes into 2 places, right? It goes here into the external tick, and it gets stored over there. And then it also goes into what actually produced the output, right? Now I want you to stop. We haven't talked about the data yet. It's not even there, right? So it's like all of this is just like from previous tick. The data will come afterward at step 10, but that's the idea. So you have the history of post-activation that get stored right over here, right? And you keep that history, and you have like some sort of like wave form that get created, right? And this is kind of important because you're trying to model oscillations, right? And then like, let's say alpha wave, there is some oscillation in, so it's 8 Hertz, like the lower pass band, and it goes to a certain point. So there's some oscillation that need to be present here. And then this is what you can use to calculate how much it is correlated, right? Functionally, or like in many sort of way to another population of neuron, right? That's the kind of the gist of it. So you have to keep an history of it just to model like that oscillation. So you see like these like plot is like it's the sample of the neuron dynamics in the CTM, and then they change depending on the input. And this, like the bold line, is like the average. So how these react compared to other neurons is the synchronization that we're trying to model. With this, what you have is what we call a synchronization matrix. These neuronal pair will be taken at at this specific step, and it will create like some way of getting a synchronization, a value of synchronization for two neuronal pair. It will be very computationally prohibitive to calculate each synchronization pair with everything. So there is some way of selecting which neuron pair will be together. In their case, they're just doing randomly, right? So because if you think about it, at the start, each neuron is kind of a soup of neurons, so it doesn't matter. And then even if you force these two to be connected, it still doesn't matter because there was no prior to them in any sort of way. And then you take these, and then you can use that differences of synchronization over time to create the latent representation. So that's the other step, is that these blocks are then used to create what we call latent representation. So the latent representation is not what's happening at one time for one neuron. It's it's the oscillation that is happening for neuronal pair here, and it's the oscillation, the synchronization that happened with them, that is the representation. So a very interesting thing that leads to very rich type of interactions. So then this latent representation can be used in many ways. It can be used as output, right? And here there's a learnable weight over there, and it can be used with an attention mechanism to create the output. And it's in the attention mechanism that the data get fed in, right? So the latent representation here, I believe, is what is the query for the attention setup. So what we get as the output that get concatenated with the post-activation is the latent representation that went through the weight, that went through the attention mechanism, that then got outputted. And this attention mechanism is mixed up with the data. So that's kind of it. And then there's a way for them to decide what is the actual output that will be, and then they have a specific way of selecting that. Now the data here, right, it doesn't just go raw into it. It goes through some sort of encoder, right? And the encoder can be many things depending on the task at hand, right? So you can swap backbones. So in this case, the backbone for visual task was, I think, the ResNet 100 and something. So this is what is being used over here, and then the embeddings of that model with the data is what gets sent out to the attention calculation. If we look at the sinus model, kind of look like this, right? So you have the output here at time t, and then the post activation that was before, and then go into some sort of kind of U-net shape structure, right? That's basically the idea, and it followed this. So you have linear layer normalization, CLU over here, and then you have this hidden representation, and it continue. You have the dropout stuff, and it just continue, and it goes out, right? And throughout this whole process, there's some sort of residual learning that is happening because you have these elements over here. Kind of cool, honestly. I don't know. It seems like they're taking all of the best bit of the different thing, and then they make it an architecture that kind of resemble be a bit closer to the brain. Remember, one of the other here is one of the other from attention is all you need. So if we look at just a simplified overview of the CTM, it kind of look like this, right? We're gonna actually see the code later on, but that's the basic idea. So if we look at the definition, we're gonna zoom in a bit. You have the feature encoder. So here, this is the backbone, and the backbone will be fed later on in the KV projector for the attention thingy that we're gonna use. The KV and Q projector are just linear projection, and then you have the multi-head attention, and the multi-head attention, it can be different size depending on the task. All of these parameters are changeable. The synapse model is basically here they're choosing an MLP, but it can be a UNet. In most cases, it's a UNet for vision stuff. and then you have the neural level model. We're going to see it in a few, what it is in the other pseudocode. And then you have the output projection from the synchronization that is a linear layer in this case. So it's this thing here that we're talking about, right? So that's the idea, and you keep track of the pre-activation history. So like this is what's happening is in the model. In this case, like they start with the data, which kind of makes sense because they can kickstart the whole thing, but then they keep track of the whole history. So you have the KV projector here, the backbone goes in, and this is the data, right? And like the data will come in again and again, multiple times, right? But you don't need to do that multiple times. You just need to do once and keep the K and the value for you, right? And then you keep the K and value here, and then you're gonna feed them back again and again in the attention kind of mechanism that you have. The Q, is what is gonna change because it is the result of the latent representation. So we have some initialization that is happening here and here. And then this is actually what we're going to start with, right? And then here it says in a pseudo-code comment, learnable start histories and first pre-attention round are learnable kind of parameters that they need to fiddle around. So this is the step that we're following. So you have the synchronization from the previous steps, right? That gets sent to the Q projector. So then you get your Q, right? Then with the Q, you can get your attention stuff, right? With this attention stuff, then it gets concatenated into the synapse with the post-activation from the last steps, right? So this is what you have, and then you keep an history of the pre-activation. So this is a first in, first out architecture, which means that like you have, let's say you have 3 slots, right? This was the first one, this is the second one that you put, this is the third one. So if you put the fourth one like this, right? This one disappear. So then you take these pre-activation history and then you jammed it for in the neural level models. So there's many models for that, right? And you jam this all there and you get like dispatch the right models. And then like you take the Z that you get out of this and you're gonna add it to the post-activation history. And remember this Z now, right, is what's gonna get sent out over here to the synapse model afterward, right? For the action, remember, so we just saw it, it actually goes here in the Q projector, right? So it goes through the attention mechanism, and then the output goes through the linear layer that we talked about. So this is the output, and you have the output history, and then this history is then used to make a decision about like what's up. So if we look at the neural level model now, it's listening to, we have this. It's nothing complicated. So we have the parameters here, the weight and biases. So it's a 2-layer. And then like we have the inputs here that are the pre-activation history up to a certain point, which is the memory of the model. And then we're just computing like the pass through it with the biases and the weights. It's literally like 2 linear layers. And if we look at the listing 3 here for the synchronization, we see this over here. So here we pre-choose the chosen neuron pair from the total neurons. So we have the number of neurons. We choose like the D number of pairs that we want to have. And like in their case in the paper, they show like a random selection of neurons. So they're doing rand_int here for the left and the right. You see here, this is what they're saying. Synchronization matrix attentional tick T for ST. So this one over here, right? In practice, we use far fewer neurons than D for separate S out and S action synchronization representation. So that's the gist of it. So there's a few kind of important elements that we're going to see in the method in a few for like the exponential decay scaling factor. But like the general flow is this one. You keep an history, so you have the history of post-activation, and then you do some transformation over it, and then at the end you get the sync representation. And that's kind of it, right? So if you have, we're going to go through it in many different ways so that you understand it fully. But it's this recursive motion that we have, and these are the elements that compose it. Okay, so here we are in the paper. You're gonna see a lot of scribbling because like I already went through it in the live stream. But there's a few elements that I want to highlight in the method that are important. So here we start with the synapse model, and they are talking about like can be many things. UNet works better in their cases. You see here that we take the post activation that we just saw, and then like the output from the previous step. And then like they did a lot of fiddling here, right? So it can be the raw output or the output that went through the attention mechanism. And then we take the M most recent pre-activation history. So this is the stuff that I was talking about like the first in, first out element. And this is our A that we have over here. And then we go into the neuron level model here. Here they're saying like 10 to 100, right? For the memory of this model is kind of good. But like it's another hyperparameter that they could test with in order to make like a push a bit state of the art for their specific architecture. So here, important, right? I think it's good to say it again, like each of the neuron have its own privately parameterized model. So at this point, like the neuron interaction doesn't cross until like the synchronization, right? So they are kind of affected by each other in the synapse model here because of how it's structured here, right? But then when we get to the pre-activation, kind of diverge, and each are doing their own thing, right? And each have their own little learnable kind of mini network. So here they're saying that we use an NMLP with a single hidden layer of width D hidden is, and then ATD is an m-dimensional vector time series. And then we get to the neural synchronization part. So the idea for this is that like here they're saying it, we want the CTM relationship with data, its interaction, to depend not on a snapshot of the state of a neuron, but rather an ongoing temporal dynamic of neuron activity, which is kind of what the brain is doing. Like it's always time bound, like how each of the neurons are reacting to each other, and like the emergent property of what we're doing has to do with how all of the neurons are interacting together through time. So this is what they're trying to reproduce, the neural synchronization part. So they have the post-activation history through time that kind of keep on getting bigger and bigger. So here they say the length of ZT is equal to the current internal tick, meaning that this dimension is not fixed and can be arbitrarily large. So as it grows, like the time series kind of grow again. How they're define the neural synchronization matrix that we saw. So this one over here is with this formula, but this is not satisfactory. You can't like it will be too much of a wasteful computation that you're going to do. So here they in order to get the kind of a linear boundary here with the amount of neurons that they have, they're gonna subsample the row and column pair in that like hypothetical matrix. So to do so, we randomly select the out and the action pair from S, thus collecting two synchronization representation, S out and S action, that can be then projected to an output space. So that's kind of the whole idea. So this is why you get from this to actually just that, right? So this is linear, this is n squared, this is what they were trying to show here. Then you get like your output, which is, it has to go through a linear kind of projection, and then your Q, which is also going to a linear projection. And then here, this is like the attention mechanism, like the other I kind of know really well because like they popularize it a bit. And then you have the feature extractor that can be swapped out here. And this is the bit that we discussed. So that bit over here. So we're going to go through it slowly. So like when you have a time series, right? After some time, it kind of like, even in the brain, right? After some time, like the influence of past elements or past like activity kind of get dampened down. They need to be kind of like time correlated. But there is also activities and brain oscillation that are happening at different time scales. So if you have alpha or you have gamma band, these are things that are happening at various time scale that you need to take into consideration when you're doing any sort of analysis. What they're saying here is that they are doing some scaling here, right? To provide the CTM with flexibility to modulate the influence of past activity, they introduce a learnable exponentially decaying rescaling factor. And I think it's important that it's learnable because, like I said, there's different resolution, right, of oscillation in the brain that means different things. This whole vector here, Rij, we then use to rescale the component of the synchronization dot product. And you're seeing we're doing like, it's still this idea over here, right? But scaled with the kind of a time decaying factor. So like that's a core idea, right? The core idea is to have like this different kind of waveform and stuff, and then the CTM can learn to alter the decay rate across different neuron pair to create kind of this population. That's the idea. However, like the model in their cases kind of doesn't use that much, right? So they say here, full disclosure, found that the CTM never leveraged this for imagenet classification, where only 3 out of 8,000 neurons per meaningful decay. For 2D mazes, 3% had meaningful decay. Anything that attacks with clear sequential reasoning warrant a more local perspective, so faster decay to synchronization. So like these first two, so the vision stuff and the maze, it's kind of like a broader synchronization type of thing. And then for like the other ones, then it was more important. So for the sixth one, that had more of a sequential element to it. And then we get into the loss, right? Which I think is pretty important. We haven't gone through the actual loss, what's happening, but let me walk you through it. So basically they can use at each internal tick, they use cross entropy. So then you're gonna have like this different output over ticks that you have. So you have to kind of find a solution to take them all into consideration. And here, like they're talking about their certainty measure that we've seen in the graph, and it's just basically 1 minus normalized entropy. Here, instead of relying on a single step, which can incentivize the model to only output at a specific step, they dynamically aggregate information from 2 internal tick, the point of minimal loss and the point of maximum certainty. And then with these two, they can take the final loss, which is the point of minimum loss and the point of maximum certainty, divide by 2. And the cool thing that they're mentioning here, I think it's worth noting, especially given the kind of the adaptive computing thing that they have going here, is that the emerging property of like the setup is that you can train the CTM without any restriction how many internal tick it should use, right? Because you can always like based on the loss, you can always decide, okay, it's good enough, let's take this one, like we saw in the example. If the certainty is high and then like the loss is good, like that's good enough. And if like it's not, and you need to have more time to think, it's still good. You can let it run up until a certain time step. So you have adaptive computing element to it. Before diving into the result, I think it's important to note that other architecture exists that share some of the behavior of CTM. These networks belong to 3 main families. The first one is adaptive computation, or like dynamic halting networks. This include early exit network, PonderNet, AdaTape, or sparse universal transformer. These architecture, like the CTM one, can modulate their compute span based on perceived task difficulty. In the CTM case, the compute budget is directly related to its time dimension, aka the number of ticks it used per data points. The second family is those of iterative and recurrent reasoning network, which include the perceiver, quiet star, recurrent independent mechanism, and the recurrent model of visual attention. The CTM novelty lies in generating internal neural dynamic from neuron history across like a decoupled time dimension, and then utilizing the explicit temporal pattern of neural synchronization as the latent representation. The last family is the biological inspired neural dynamic networks, like liquid time constant network or the spiking neural networks. While inspired by the principle behind like spike timing and neural synchrony that are used in these networks, the CTM abstract some of these dynamic, focusing on local temporal integration and population level synchronization instead. This makes the framework that they're using, the CTM, differentiable and tractable. It helps a lot for gradient-based deep learning. So it's similar to these in a sense, but distinct in implementation because they favor practical implementation. Interestingly here, reasoning models are kind of bootstrapping the temporal processing and synchronization bit of CTM in a very crude way. If you have a transformer model using intermediate step to think and to feed them back within itself, it kind of create a pattern of activation that are in a way encoded and distilled in the intermediate output. It also uses more time for a given task because you have to go round and round into the processing through the intermediate stage. In a way, the reasoning models that are very current right now have these properties that are interesting from the CTM that add them out of the box. Anyway, let's see how this architecture performs on vision experiments. We have a few to cover. So here, do note that in this research, the author were not after getting SOTA result. This paper is a feasibility study with a common vision benchmark to review the design choice and to assess whether they made sense or not. So the first result is the imagenet 1K class classification. The task is basically to learn how to classify an image on 1,000 different classes. ImageNet, ResNet 152, that's the backbone. In this plot here, you have various things. You have the percentage of data that has positive or negative kind of outcome, and then the number of internal tick. And it's a bit weird because with one tick, you have 60% of data that has none of them, because the model didn't decide to do something. It didn't go through the threshold to make a decision, right? And you see here, there's a bigger amount of negative, but as we go through here and there's a threshold is higher, there's even lower element where we're actually making a decision, but the red stuff is lower. So what it means here is that sometimes the model didn't have enough time to output something, right? To think through. So the certainty threshold is very low. So in this specific case, the model just shut up and didn't do anything, which is very interesting, right? So like you don't have that out of the box with some of the architecture, but in this case, it can dynamically decide to just not output anything. And here in this plot, you have the top 5 accuracy element with the number of internal tick, and then there's many ways that strategies that they're choosing in order to output something. And like what it just says is that after some tick, you just need to take the most certain. So you have a way to decide which element to output, but you also have a way to say like, should I output anything based on a threshold that you can modulate. And here, this plot, a bit hard to understand, but basically it's like how many of the data points have 80% certainty threshold based on the number of ticks. So most of the data points can be figured out before the 10th tick. You don't need to do 50 for all of them. Some of them, the certainty is like so high right from the start because the data is not that complicated. So if we look here, the certainty for this one is high, so it's before the 10th tick. And this one, like, it's struggling a bit, right? So the certainty is like not there. So we need a bit more tick than just that. Here, with this plot, what they show is the post-activation neuron dynamics. So this is like the history that get created over time. Like this is for each of the neuron, and then you have the average of it. So like if you look at it, some of them have a very specific kind of way of responding, right? And then some of them are kind of like across runs and across data point, like a very hectic thing. You can average them out to see roughly what's happening, but this is the stuff. The cool thing that you can look at is like, look at all of these, right, that have like very specific one, and look at others that are a bit more dynamic, and take a step back. Like that's very dynamic. And if you looked at the brain in different areas, you will see something similar. Like not all neurons are firing at in the same way, or not all even population of neurons are firing together in the same way. But then they interact with each other in the various ways. The other thing I want to show here is this one. So this is like on ImageNet, all the neurons, right? And they have this shape, but like it's a UMAP, right? So it doesn't matter like the actual positioning. But what you see here is like pattern. It's a video. It's like a pattern of oscillation of neurons. And then blue is like they're not very activated in here. Red means that they're very activated. And you see kind of these waves flown into this whole network, right? The geometry of it doesn't matter. In the brain, it does, because stuff that's in the occipital and then on the prefrontal cortex, like the geolocalization of them kind of matter. In this case, it kind of don't. But what you see is a dynamic representation as they're looking at the given images, right? Which is very, very rich. And like this thing that you're seeing, like this dynamicity, synchronicity, you're seeing it live in the video, but this is what the model is using as its latent representation to actually make a decision. Yeah, super cool stuff. And this is what they mentioned in the paper. We consider low frequency traveling wave a phenomenon widely documented in cortical dynamic and implicated in various neural computations. So this is the alpha, beta, gamma, whatever wave that I've been talking about. So that's pretty much it. Like the performance of this is just okay. It's good. It's not like the best ever, but it's just okay. Let's say at 50 ticks, this is like the result that they're getting over the 1000 class classification problem. The second experiment is to solve 2D mazes, like we saw before, using limited movements output and with no positional embedding added to the data. So what we're going to see here is that you have a CTM with the ResNet 434 backbone, and what the model is outputting is at each neural tick a matrix that defines a route from the start location. So at each time tick, it should output like the full route that it will take. And they're comparing this CTM with the LSTM baseline and a feed-forward only with no recurrence model, so fully connected feed-forward model. So here we're seeing the various model with the number of training iteration. So here after the number of iteration, you see like the final kind of output here, the one in solid. And as the path length increase, right, you see the different accuracy. And the CTM is the one that like doesn't have that much of a degradation. So even if the path length is smaller, it's doing good. Even if it's higher, it's doing good. The other one kind of degrade as the thing get bigger and bigger. And here we see something that is kind of an emergent property. So like even if it was trained, let's say for 100 step, right? If you do something that require 200 step, and then you let it run over it, so it was not trained on 200 step, it learned to look ahead, basically, right? To be able to find a solution. So this is what you're seeing with I would say like this little path that is creating. Show how the CTM continue to attend to along the route, even beyond the internal text used to train during training. So it kind of learned something, right, about like an algorithm to be able to do that in these maze. And it has to do with the text that it has, but also has to do with like how far the thing that it need to it is, and then like the attention mechanism will look there instead of looking like only at 100 ticks and stop there. And then after that, like they did some cool stuff where like this is the 39 by 39, so this is what it was mostly trained on, and then like they just bumped it up, right, to 99 by 99, so it's much bigger, right? And with this, they were looking at like the dynamic of the model and like its performance. So with the 99 by 99, the root length can be like much bigger. And then here is what you see the degradation. So at the 39 by 39, the model is pretty good. So here you see a degradation with the 99 by 99, and like, but you still see some performance. But as we go bigger and bigger, the model kind of collapses. It is generalizing, but it's still struggling. And that's kind of where they left it off, right? So they did a bunch of things. So reapplication, so they kind of restarted the model start position multiple times. Kind of doesn't matter. The interesting thing here, I believe, from the maze thing is this. The model kind of learned to generalize beyond training, and they pushed it to the maximum, which I like, to the point where it's completely broken with 99 by 99. It does find solutions sometimes, but it does get lost when it was not trained to this extent. In the next experiment, the CTM was compared against human performance on Cypher 10, along with the fully connected feed-forward network and LSTM models. So they're using the feed-forward baseline, the LSTM baseline, the CTM, and the human performance. So during this whole thing, they have 50 internal tick to give the CTM and LSTM. Honestly, every time they give ticks to LSTM, it just breaks down. So you see here the different training curve, and here they said that the calibration plot show that even a human baseline is poorly calibrated, and that the CTM demonstrate good calibration, failing in a way that is tracking similar to humans. So you see here the human average is this one over here, and you see the CTM that is kind of following a similar trend, a bit like the LSTM is doing. The fully connected feed-forward is failing in ways that is not like really human-like. That's what this plot is roughly showing over there. So here you have the training curve for like the LSTM, CTM, and then fully connected, and you see that the CTM is the best here after this many iterations. And like here, depending on each of the elements in the dataset, you can see like the level of difficulty. And here you see that like the CTM follow kind of a similar trajectory to the Cypher H, so the humans, but like every one of them kind of follow that. Even the fully connected here, the average one follow the CTM in some way. And here you have a measure of uncertainty versus difficulty. So the measure of uncertainty is based on the number of millisecond or the number of tick it used in order to make a decision. And as the difficulty increase, you see that the time it takes is a bit longer, a bit like the human. The LSTM also is a bit like that. So these two plot kind of doesn't show much. I think the one plot that is making an interesting point is these ones where the CTM neural activity is very rich, And the LSTM one is a bit more flat, right? And it, like you see here, this one, like I don't see this one. Even if it's average out, I don't see it. Like the neural activity that is happening in each of the neurons is not as diverse and not as like well defined as the CTM. One thing though that I think they could have done better here is quantify this, right? Let's say that the STM yields some dynamic behavior in the post-activation history, but not nearly to the same degree. They could have found a number. I think that would be cool. Qualitatively, I think it's nice to see, but quantitatively, I think they could define this the how to say it, like amount of diversity of activations. Next experiment is an ablation study to figure out what happens when ticks or number of neurons are modified on the Cypher 100 benchmark. Basically what they're doing is here you see the model width, you see the accuracy, and you see after some point the model doesn't have to have many neurons. You don't have to have like a lot depending on the task, right? So here the best accuracy is with 500 neurons. If you have like way more, 4 times more, you don't get more accuracy, right? You get a bit lower. Here the two other plot that they're doing is neuron similarity across data, and here neuron similarity across neurons, right? So what you see here across data point is that as the width increase, there is a tighter curve around closer to 0. It means that the neurons are a bit less dissimilar when you have a lot of them. Well, when you have not that much neuron, there's a constraint here. You have more dissimilar neuron because the dissimilarity create better latent representation in some ways. Right here they're saying, indicating that the CTM can encode more information about the data point in its neural dynamic when there are more neurons to work with. Then you have like these two plots for Cypher 100, which is showing like the thought step and the accuracy. So how many steps you let them think. You see here that like there's the accuracy is highest at 50. After that, there's a drop off because effectively what they're saying is that there need to be more training here. So which is encouraging, meaning that like if you train these models like crazy, they should have some scaling associated to them. And here you see the distribution of where the CTM is most certain, right? Depending on the thought step. And this is per percentage of data most certain in this step. There is two distribution when you have, let's say, the 50 and 100. So there's a very big spike here, right? Where like after 10 or 20 steps, the model is pretty certain. And then there's some that are harder and need more time to think. These ones are the ones that require more data, right? These ones don't, right? These ones are easy. So the model doesn't need that much to be able to tell that this is good. But these are the ones it need to have more time, and also it need to have more data to be more certain because they've seen it before. So it indicates some sort of sparsity in the data set about like some feature or some element of it. The next experiment was a short number sorting one. The goal was mainly to compare with RNN how the CTM is constructing its internal algorithm for the task. So basically the task is you had to sort 30 number, draw from a normal distribution, and then output them sorted. So here they're using the same trick as the maze. Like at each time step, the model need to output like about 30 element, 31 actually, but doesn't matter. So 30 elements that represent like the element sorted. So all these plots, what they're trying to say is that like the model has some wait time per indices in order to say like to make a decision about where they should go, and the one that has longest is the first one. You can see an evident pattern that the average wait time, where the initial wait time number of virtual tick is high, goes to its lowest point and has slightly higher bump toward the end of the sequence. So it's kind of need to look at the whole thing before making a decision for the first index. Here we're seeing the wait time versus the change in sequence value, and they say that the CTM employed various wait time, but that the difference between the previous output value and the current output value, so the delta, impacts the wait time the most. And then this last plot took me so long to figure out. So you have a lot of going on. So like you see these bars right over here, right, colored in the rainbow colors. It's the actual element, and then what it means is here is that purple one is the smallest, and then the red one should be the biggest. So like it should be the color of the rainbow. Do you know like the actual sequence of the color? I don't know. So like when I look at this plot, I have no clue what's the sequence. I know that this one should be like some of the first, and these ones should be some of the last. But anyway, so this is the stuff that is happening. Red means there's a bigger than usual wait time, and green means that like there's a smaller than usual. So you see these two elements, these two numbers actually are kind of close. So there's lower than usual wait time, and but this one, the green and the blue here, they're kind of very dissimilar. So there's a big wait time here. So this is what it kind of show here, which kind of align with it having developed an internal algorithm for that sequence. Then the other did a parity experiment, which Arnon usually excel at. They modified the number of tick here to see how the model modify its internal algorithm. And basically what you have is an input sequence of 64 binary value, top left here to bottom right. So it goes like this in a snake-like fashion. And this is the input, this is the target, the cumulative parity at each position, right? So you have to figure this out. So look at, because like here the parity is the sign of a product of its element when you process them sequentially. Here you have -1 and 1, that's what you have, and then you have to compute the parity between them. So here -1, this is a positive, right? And then you have another -1, this is a negative. And then you have a 1, this is a negative still. And then you have a -1, this is a positive now. You see, this is the kind of algorithm that you need to kind of do. And like this whole thing is fed at once. And the model need to figure out how to calculate the parity at each of the element and output the whole thing all the time at each time tick. We actually see it quite well here, right? On this thing. So this is the target, right? And this is what it's doing. And this is how it's making the parity, and you even have like the little brain making its wave through it, and to see like the prediction. And you have the attention heads here doing their work. So again, CTM versus LSTM, and then you see here after that much iteration, the CTM is kind of dominating here with this number of iteration. So when you have 100, it's like way above LSTM. The LSTM kind of just is not that good with more ticks, right? Like you see here, it's actually worse when you have a lot of ticks than when you only have one. It was not made to have ticks. And you see it here clearly, like as the number of tick increase, it's getting better and better, up to 75, which makes sense. And then the LSTM actually is just getting worse. So like the whole thing is that the accuracy can increase when it has more thinking time. And their main claim here is that it actually learned an algorithm to be able to do it. And like you can change the algorithm based on how much thinking time you give it. If we look at it closely, when you only have 10 internal tick, right, you can go up to, I don't know, 30 sequence index, but then it falls off, which makes sense because it doesn't have enough ticks to do the stuff. And at 75, it just has enough time to always get it right. Even with like 64, 65 sequence length. Let's now look at like two different CTM that they've trained. One with 100 internal tick, another one with 75 internal tick for a 64 digit element. What we can see here, the 100 is that as the training is progressing, right, it has learned to look at the first element at the beginning, and at the end, look at the end. Right, so it kind of scan through them in order to do the parity thing, right? With 75 internal tick, it's kind of a bit the opposite that it's is going at. It's looking at the kind of last element, and then further down in the elements here, especially when the training is like at 25%, and then like looking at the first one. So it's kind of going into the reverse order and bringing everything together kind of at the end completely to put the whole solution in one shot. So this is interesting because it changed its algorithm based on how many ticks you can give it. And you can see still with the attention heads how it's moving. So here this is a typical element, and you see all of the heads looking at different stuff. Some of the heads only look at the blacks, some of the heads look at the whites and blacks. So they kind of have different zone of expertise. There's a failure case where everything is white, thing completely break down, not able to do it. So even then, in edge cases, it's still struggling. So its algorithm is not necessarily like 100% the best here. The next experiment is kind of a fun one. I think it's one of my favorite here. It's mnist, but with a modification to involve learning a sequence of operation. So we can see it here in a visual representation here. So at first they're gonna see the numbers that are implied in here, and then they see like the different manipulation they need to do and the different index of what we just presented, right? Here you see the dynamic of this mini brain, and at the end you see like the certainty here for each of the element, and you see the certainty kind of oscillate while this thing is ongoing, right? But at the end, the last mod 10 bring up the 9, which is the actual answer. Here, the interesting bit is that the memory length of the 1 and 10 interval tick per input CTM were set to 30 and 30 steps. So we highlight that with these observation and memory length, the configuration that the digit observation will always lie outside of the memory length size window during the answering stage. So it's not like memorizing, really, right? It's like, well, kind of, but there is storing the information not in the predefined block, but in the oscillation dynamic in some ways. Pretty interesting. So you have the LSTM, the CTM again with the multiple iterations. So the LSTM, you can forget it. And you see that the CTM is kind of pretty good at 10 iteration, and then at this number of training step, it got it perfectly understood what's up. LSTM is still good, right? The LSTM kind of is made for the sequential type of information, but CTM is able to catch up with the 10 iteration. So here, with a single internal tick, the LSTM initially outperformed the CTM. As the number of internal tick increased, the LSTM performance degrade and learning become constantly more unstable, which makes sense because they were not made for that. In contrast, the CTM constantly improve its performance with additional thinking time. Right, so this is kind of here the number of digits that they need to memorize, and here the number of operation they need to do. And this red thing is what it was trained on, right? So this is CTM with 1 tick. This is the LSTM with 1 tick. So this is CTM with 10 tick, and LSTM with 10 tick. 1 tick, LSTM is better. Like it generalizes even better here, right? It doesn't generalize with digit, neither this one, right? So none of them kind of generalize better with digit. Well, you see here with the 10 internal tick, the CTM, same kind of thing here, is much better with more operation, even better than this LSTM. Don't need to look at this one, honestly, because it kind of doesn't matter. The LSTM is getting confused when you give it more ticks. Interestingly, none of them can improve past number of digits. So there is some algorithm internally that made it so that they were storing in some way, in some shape or form, the 4 numbers here somewhere, right, in the oscillation or something. So when you try to increase that, it never saw that, so it kind of get confused, which is super cool. I don't know why like this thing is the number of operation doesn't matter because they don't need to store it in memory in some form. They just need to apply it, right? And you see it in how they're doing their prediction. The prediction is kind of related to where it's at in the sequence. Yeah, I think we saw it here. So the best more certain element here is related to where it is in the sequence. So here the 2 is the highest, because if we stopped here, it would be that. In this specific scenario, you really don't need to save in memory the operations, right? Because they are consumed. The numbers though, you need to do that, because like these index tell you which one you need to fetch, right? So if you develop your old encoding for 4 numbers and then we give you 5, of course you're not going to be able to recall it, because in your latent space they are not properly stored. Here we find that the model compute each part of its composition sequentially as the embedding are observed, with output 2, 1, 9, and finally the correct answer of 1 projected from the synchronization representation. Like this specific study, I don't know why, but this one is one of the coolest of all of the bunch. Even it's not as flashy as the maze. I think it tells us something very interesting about these models, in that they kind of can have a rich world model kind of representation of whatever task they are being worked on. And the last experiment is one involving classical reinforcement learning tasks like cart pull or acrobat. And here what they're effectively showing for like the cart pole, acrobat, and mini grid is that the CTM is kind of good. It's very hard to see, like it's and the cart pole, like it's not that hard of a thing, but the CTM with one iteration is kind of okay, but then with 5 it's like much better here, right? And especially with like more unribbon step, it's better and better. Yeah, so that's just the idea, and it's as good as the LSTM. For the acrobat, the LSTM with 5 iteration is poor. At this point of the paper, you get the idea. LSTM, more step, sucks. So you just really have to look at LSTM 1 and then CTM more than 1. So CTM more than 1, you get like a very few episode length here for the acrobat, which is, it means it's better. Same thing for the mini grid here. It means that like as it goes lower, it means that you're able to clear it up a bit faster. CTM 2 iteration, and get as close as the LSTM here. So basically it can do what the LSTM can do. So let's now check out a notebook on how you can start tinkering with the architecture yourself and to dive a bit deeper into the implementation. Two in particular are interesting, the inference and the mnist, because in the mnist they show like a dumbed down version that is a bit more not dumbed down than the pseudocode that we saw earlier. So in the inference, it's fairly simple. You have this whole notebook that you can clone, and what you're gonna get here is a link to a zip file in their Google Drive with some already preset weight for you. So here in this case, it's for imagenet with 4,096 neurons, 50 ticks that they will run this stuff through, and a memory of 25, right? So that's kind of what they have over here. And then you can load it. It's a PyTorch model, so it's nothing complicated. And you can load any image from ImageNet, and it will be able to tell you what's up. You're gonna have to transform the image like it was during the training. And here, this is not too important, just to make the GIF to be able to see it. So a lot of engineering went over there, but at the end of the day here, you see this stuff, right? Exactly like in the paper. The model is actually doing all of the stuff during these ticks, and you can even see like the neural dynamic with this nice plot, and you can see for each of the subset, let's say, of the neurons here. And now for this one, I think it's the most important because it actually holds the CTM, and then you train it from scratch with all of this. So we do require some bandwidth, but they dumbed it down enough so that you can pretty much run it with anything, and like it's mnist, right? So it's not the most complicated task. So we're gonna go through it in a few, but this is the continuous thought machine, right? This whole thing, it goes over here. It looks scarier than it actually is. And here again, you have the training loop, and we're going to be able to see, and then here you see the loss as the step increase for mnist and the accuracy increasing. And then you can make the same GIF, which is pretty cute, right? Which are over here, and then you see, give this data point for 50 ticks, it will think. So if we take a look at the implementation, there's 2 buckets, right? So there's the stuff that we're going to use and the actual continuous thought machine. So this stuff over here is a layer that we need for the NLM, so the neuron level model. So these guys over here, and it's just one of the layers, right? So you apply dropout, you have the W and B parameter, and then they use Einstein summation like we saw before in order to stack 2 of them together to be able to do an MLP. So that stuff, this is what I'm talking about over here. The rest is fairly straightforward, no need to worry about it too much, and this is just to calculate your certainty, right? So you have the normalized entropy here, and this is how you calculate it, and with this you can calculate your certainty, which is 1 minus that thing. If we do look at the continuous thought machine, right, it looks like this, right? So you have all of the parameters that correspond to like these that we see over there, and like the ones that are composing them. And here we start to see what's happening. Remember, this is for mnist, which is a very simple kind of problem. So here you have your backbone. If it was ImageNet, this will be like ResNet 152, but in this case, it's just like a small convolutional neural network. This will be used when you're going to do that bit here, right? So this is used over here just before the KV projection, so that you can get the embeddings from your data, right? And you can do it this just like once per data point. Then you have your attention heads that are multi-headed attention, and you say how much you want. And this is your KV projection that will be used with your backbone. And this is your Q projection that will be used with the latent representation over here. And this is that stuff over here. Then with this, you have the science model, which is a pretty simple model in this case, because it's mnist, right? But remember, they said in all of their tasks, UNet was always better. So this is not a UNet, so this is just a sequential layer. And then you have the trace processor, which is a weird name for what it actually is, because this is the NLM, right? So you have your super linear layer that we saw just previously, so that thing, and they just call it trace processor. Maybe like this thing changed while they were going around and setting the architecture, so this may be an older kind of notebook. So you have your two layer MLP here, and then you start to do actual stuff. So this is the starting state, right? And then they initialize it like this, and then they register the parameter, because you're actually gonna learn them. See here, require grad true. You're gonna learn the state. You need to do that even though you're training, because when you're gonna receive an image, you're gonna be at step 0, like so, the state 0. So there is no there's nothing in these, right? So what do you do if there's nothing in these? You have to have initialization that makes sense, so that like you're in the first tick, you're not completely random. Otherwise it's unstable, right? So you require true for both of this. So this is like the activated state for the pre-activation, and this is for the post-activation, I believe. Then there's the setup for the synchronization, and then you set the synchronization parameter here, which is just a helper function, because you're gonna set it here and you register the parameter. So you're actually gonna have to learn these two, the synchronization parameters. And lastly, here you have the output projector here for that bit over here, right? So you need also to have that. And that's kind of that, right? That's the whole setup, right? We can look at these or look at the forward. So we're just going to go through the function here, nothing too crazy. So depending if you're doing the action, so for the attention or the output path, right, depending, you're going to do like set up your variable properly, and then you're actually going to do it. And if there's a decay that is set up, remember in maze and imagenet it was kind of useless, but the other one it was useful when you have sequential data. Then you have your R that we discussed that is used to decay the very older element. So to get like and this is learnable, so you're gonna get like the different type of frequency waves going through the network. You see here, and the set synchronization parameter, it's a decay parameter that we are setting. Right? So decay parameter for action or decay parameter for out. And then here, this is how we compute the feature stuff. So to get our KV, so it goes to the backbone first, and then once it goes to the backbone, you have the input feature, which is like the kind of embedding stuff that get shoved into the KV projection. So in this case, we're doing this stuff over here to get our KV, and the Q comes from here. This is how we compute the uncertainty. So this is the normalized entropy that we saw before, and then you do 1 minus the normalized entropy to get your certainty. And then when we look at the forward, where most of the action is happening in actuality, we are setting up some some of the arrays that we have, and then here this is where we're actually going to do like all of the steps that we need, right? So this is not for the training, this is for the forward. So if we have many ticks, we're going to do many iteration of this for loops. So we calculate the KV just once, don't calculate multiple times, it's wasteful, just once, it won't change anyway, right? So you take that, and after that, this is what you're going to manipulate. Later on, some storage initialization stuff going on here and here, and this is also the first initialization that we need to do. Then we do the action, right? And here it's like at first you calculate the synchronization for input data interaction, and then you do you take this synchronization, right, and then you're gonna apply it to your Q projection. So basically, you did this, right, and then you got that, and you did this. That's what's happening here. Once you have that, you have your attention out, right, which is the actual O out that you're gonna give to start the loop, right? So yeah, you have to do that first in order to have it. You jam it in here, right? And then with that, you're gonna start and then have this presynaptic activation, right? And it goes through the synapse model that we saw earlier. Once this is happening, you shove it through the trace processor, which doesn't mean that it means in the LLM, right? This is, you shove the presynaptic thing into the LLM, and the LLM is many of them, right? And it's important here, the N is the number of them you want, and then it goes in here, right? So you're gonna get like this kind of 3D tensor, and in this thing, the N is the dimension of the model. So the dimension of the model is how many neurons you want to have. So N is effectively how many neurons you have, and each of these are like the learnable weights, and you're gonna shove the input in there in order to, for each of them, have their own little Einstein sum that they will go through. So that's that for this post activation. And then once you have that, you're gonna calculate the synchronization for the output projection. So again, compute synchronization like we just saw, but now with the output instead of the action. You're gonna get all of these out, and these goes into the output projector and the certainty stuff that you're gonna use to decide what to do, right? So the output projector is this. So you get this now that you're gonna shove here for the output, and the certainty that you use to decide if you stop or not. And that's kind of that. And then you're gonna add this to your prediction certainty to track it forever. And that's pretty much it. That there's nothing else to it, really. That's the whole thing. The paper kind of end with like very interesting tidbit of information, specifically for like this type of modeling. I wish to move toward training the CTM in a biological, plausible fashion for it to work. So with the video, text, sequential data, this is how we see the brain, the world is like with sequential type of thing. Particularly when sample in order during training is a promising avenue for future work, and they also want to do that with text and to do language modeling, which I think is pretty cool. To create kind of these word model within the CTM and do kind of the pre-training thing. One thing though, right? If you read to the end, one thing is that like the core architecture kind of stay the same, and then you just need to pop in, pop out the various like output input. If you read the paper, you see these encoder getting popped out for the different embedding, and then like these output being just like changed based on what it's needed. But say here a very important limitation thing. The main limitation of the CTM is that it requires sequential processing that cannot be parallelized, meaning that training times are longer than a standard feed-forward model, particularly when considering that the current state of modern AI model are well suited to the hardware and software that has been developed in parallel. Right? This is pretty heavy. Like I think there's still work to do on the architecturing side. Yeah, I mean like there's still work to do either on the architecture side or how we're modeling and letting these model kind of be, right? I don't know. I feel like the time synchrony of it, like as soon as you add time into the mix, what you effectively do is like you kind of remove all the advantage of having like a silica brain, right? Because if this is time bound and it needs ticks and it need times in order to learn something because of the pre-post synaptic thing, I don't know, man. You may be much better getting like an actual brain and training it like right here and then than to try to train something in silica, which will take more time. You could have more neurons, I think, right? And maybe that will be that. Maybe like if these type of models are very like much more powerful, but they require a time aspect, maybe we're gonna see like these massive model being maybe like for like 5 years and then after the fifth year, they start to rapidly scale in how they're configured and stuff. Yeah, I think there's still stuff to do here in the architecture side. This research is still ongoing, right? So it's like we're doing it live, right? We're doing live. Here the other I would suggest you to follow him, very smart dude. Here they show the latest thing that they've been able to do, which is to create a foveate activation function, which is kind of like what happened with the retina of the eye. So kind of like where to look at and how to look at for kind of each neuron. So basically what they're doing here is that they enable foveate vision. So the fovea is like a center of your retina is like high resolution. Everything else is kind of like low resolution. So here they get the small fovea, focus, and a compressed low resolution view of the periphery, and it allows them to dynamically choose between examining detail and understanding context by deciding where to look, kind of like some focus area that you have. So this is like what the model is getting imputed, and if you see here clearly there's like some middle thing moving around, which is where it's focusing. So you remember like the arrow thing that we were seeing? This is the same thing, but like with this fovea instead. And then like this is what they see, and they're just like projecting back to something that we see better, and it's literally that. So this is like the periphery, and then like this is the periphery, this is the focus area, and like here you see all the attention head like looking at different things at different resolution. Anyway, like cool stuff. You cannot say that this is not cool. So I hope this was useful. Don't forget to like if it was the case, and see you all in the next one.